my collaborators and I are interested in effects. In particular, we're interested in how to structure our programs to define new effects. And doing this talk, I'm going to use as a running example, just adding a single bit of state to a language that might not have any kind of mutable capabilities, any kind of side effects. Okay, so the programs we want to write programs like the one on the left-hand side, where we have some operations for getting that bit and maybe mutating it and flipping it and then putting it back. Okay, so we want to get it and then change the state and return what was there previously. So we're just toggling the bit. Okay, and if we don't have side effects in the language, we can encode this using state passing. Okay, on the right. So this is a very old technique. Okay, so our computations are now state passing. So if you give me some initial value s, I will give you back some result and the current state. So the get operation just returns the current state and doesn't change it. And the put operation takes as input the new state, ignores the current state and returns and flips or changes the current state to whatever you've given it. In order to run one of those computations, one of those toggles, right, what we do is we take the computation, lambda c, and then some initial state s, and then that computation is thunked, so we force it. This is what the bank means, forcing the computation, giving it the initial state and running forward with it. Okay, and then we can express the toggle computation almost as we would otherwise, as we wanted to encode it. But I've tried to encode this as closely as possible to the intended computation, but still there's quite a lot of noise that we have here. So we have to introduce some pattern matching at every point where we might change the state or might inspect it. And so the key problem with this translation is that it's a global translation. It goes over the whole program and it has to find the points in which we manipulate the state and change it globally. So it's not a local translation. The second problem with it is that it doesn't preserve the core construct that we had. So we wanted to just add get and put, but somehow we also had to change this variable binding. Okay, so we turn a variable binding into pattern matching as well. So I'll try to use syntactic shortcut to make them seem closer, but they're quite different. And so this issue of not having these two properties was investigated in the 90s by Matthias Verleisen, who might even be here. It's called macro-expressivity, and we want to be able to express these new features, this get and put, using the old features by having a translation, by translating them away in a way that's local and preserves the core constructs, the old ones. Okay, so this is the notion of expressivity that we'll be investigating today, and we'll be comparing and contrasting three different ways of encoding effects, of defining new effects in the language, and I've listed them in most recent to oldest ones. Okay, so we've been having quite a few talks about algebraic effects, and I'll be talking about them in a minute. And monads are well familiar in ICFP, so Spivey and Wadler, following the work of Moji, and delimited control, which is been an old way of encoding effects. Okay, so I'm going to be comparing and contrasting these three ways. Okay, and if you really want to take something with this talk, you have to pay attention to the small print, and that's really crucial. Okay, so the first thing is that the design space is huge. Okay, so what I'm presenting here is a point that we believe is the starting point. Okay, and it's a high-dimensional design space. So you can change the notion of a handler, you can change the notion of a monad, you can change the notion of a limited control, and what you get is a different language, and the interrelationships might change. In particular, if I'm giving you a result, if I'm explaining a result about inexpressivity, once you change the language, all bets are out, and you might be able to encode effects that you couldn't encode earlier. Okay, so if anyone tells you, oh yeah, I can do X because I have Y, you have to be very careful as to what exactly they're using when they're encoding X using Y. Okay, so the takeaway message is, if you want to make any claim about expressivity, first define the source and the target as formally as you can. Hopefully there's some kind of abstract calculus, you can actually fit it all in your head. If not, maybe use a theorem prover. And second, make formal proofs about this. Show that the translation is macro using those formal proofs. Okay, so if you take anything from this talk, it's this. Be very dubious of anyone claiming, yes, of course I can do X because I have Y. Okay, so what's in the paper? what we did is we started with a simple lambda calculus that's compatible with effects, and that's Paul-Levy's call by push value. And we extended it in 3 different ways. We extended it with algebraic effects, we extended it with delimited control, we extended it with monadic reflection. Okay, and to give you more assurance as to the more syntactic properties of our formalization, of our development, we formalized it in Abela, and we formalized all the lightweight things that you could think of, all the sanity checks you would think of proving about your language. So things like progress and preservation results. And as I list the contributions, I'll be highlighting what was formalized in Abela. Okay, so once we define these 3 calculi, we define macro translations between those calculi. Okay, and some of them were already present in the folklore, never between all 3 languages in the same setting. But in particular, we have 2 new translations, the one that are starred. Okay, there was no translation we know between monadic reflection and effects, between monads and effects, so effects expressing monads. And we have a new macro translation that can express effects using limited control. The existing translations are not macro translations. So this is something new we're adding here. Okay. So these calculi are untyped. So we also include a type system for each of the calculi, the natural type system that you come up with once you know how to program with these abstractions. And for the ones that haven't nice denotational semantics, so algebraic effects and monads, we also gave a denotational semantics, a set theoretic denotational semantics that is adequate and sound, so the basic properties you'll prove about denotational semantics. And we've also, as I said, shown type safety formalized in Abela. Okay. Then we repeated the same question. Can those typed calculi be macro translated? So in particular, if we look at these translations, do they take typable programs to typable programs? And again, you should be dubious because I'm saying typable. There could be lots of other claims that could be making about these translations, and you can come and talk to me afterwards. So the precise statement is, if I have a typable program that can have a type, do I get a program that could have a type at the other end of the translation? And so we've shown that monadic reflection can simulate delimited control and preserve typability. So this arrow preserves typability. We've also shown that there can be no macro translations along these arrows, along the arrows annotated with doesn't exist. So not only the translations we have on the left are not typability preserving, there are no such translations. Okay, and now your warning sign should come up, and the proof we have is very, very specific to what we've put in our core calculus. In particular, we didn't include inductive types, let alone recursive types. Once you add those, our proof goes out the window, and you have to think carefully whether it is or it is not. Okay, so as we go by, I'll try to give you some intuition why we think this result is a bit more robust, or how you could take those non-exists away. But the precise statement is the systems I'm going to describe cannot express each other along these arrows. And finally, we conjecture that the other arrows, the ones we did not find, we did not show you, don't actually exist at all. Okay, so in this talk, I'm just going to talk about the translations, and if I have the time, I'm going to talk about how we prove the inexpressivity result. Okay, and again, the takeaway message is, you can see it very clearly here, if you ignore the types, everything is fine. But if you come down and check whether the typing rules you had up front guarantee that what you get at the other end is well typed, that falls to pieces. Okay, so be very dubious, very suspicious. Okay, so we're going to start with effect handlers. So we're going to give you the pragmatics of the language. So if we're looking at our state example, what we have with effect handlers is we have as primitive operations in the language, we have names for effects, get and put, and we can use them to write code that manipulates effects, that call effects. These effects have no meaning, and in order to give them meaning, we define a handler that gives them this meaning. Okay, and we're using almost the same trick as we had before. To handle a computation like this, we turn it into a function that takes some current state and manipulates that state. So what does the handler say? If you have a computation that just returns a value x, then just take the current state and discard it. You don't need it. Just return the result. If you have a get, then the get doesn't take any arguments. but you have some continuation at the point of get that expects the results. So you take the current state and you pass it as the result for the continuation. So this is what we had before, but we just write it inside the handler, not inside the computation. And similarly with put. Okay, what does the run state function do? It takes a computation C and it handles it with this handler. Okay, so if you just run it on a simple program that starts with the state true, what you're going to get back out is true, but just before you return true, the currently stored state was false. So we toggled it. If we develop a type system for this, then it's a type and effect system. So the natural abstraction is a type and effect system for effect handlers. And what the effects denote is the current sets of operations that you can manipulate and what the signatures are. Okay, so get doesn't take any arguments and give you back the bit. Put takes the new bit and gives back the unit type, but changes the state. That's the intention, at least. Okay, once you have this annotation, then we annotate the computation toggle as a computation that returns a bit, but it's tanked, so we have to run it later. If you're programming in Haskell, this will be the state of bit, state monad of bit. Okay, and similarly, run state would be, the handler would be a handler that can handle computations returning a bit and perhaps causing get and put, and then it handles them away. So there's no effects after you handle them, and you return a function that, given some initial state bit, is going to give you back the bit. Okay, similarly for run state. Okay, now let's look at monads. This should be more familiar to the audience here. So here, get and put are defined operations. Okay, so they're not primitive, they're not pieces of syntax. Instead, what we do is define monads, like the state monad here below. Okay, and I'm going to say a few more words about this syntax. Okay, so you define a return function and a bind function. This is the usual state monad. Okay, and then when you write your computation, at the point you want to access the state, you graft in some specialized information about what is the ambient monad. So this is what's called monadic reflection. Okay, so if you look at the literature of monads, they're usually described as an encoded abstraction through type classes or implicits. Okay, but if you really try to look at the literature, so at which piece of work study monads and abstraction on their own, what you get is Felinsky's monadic reflection, which uses this reflect operator. This is the one we've used. Okay, so whenever we want to actually access the state, access the effects, we reflect into it. Okay, and then at the end, in order to run it, what we do is verify the computation into, in this case, a state transformer, using the verify operation. And that gives us a function that once you give us the initial state, is going to give you the final state together with the result. Okay, and the type system, it's almost there. It was there almost all of it. So our type system, we have to be able to encode monads in our type system. So our types now contain those returns and the binds, but it also tells us that the monad is somehow a parameterized type. Okay, for each alpha, I can give you back a straight transformer returning an alpha. Okay, and so let's give an example of a translation from Mon to F, or the translation we have in the paper. So monadic reflection is going to be just a single operation called reflect. Okay, so we have a single operation called reflect, and it does all the work. Okay, so reflection is translated into reflect. Verification, it becomes a handler that puts in kind of the limits until what point do we have to reflect. And then when you return an X, you're going to use the return clause of the monad, NU. And when you reflect, okay, if you look at the exact information you have at the point of reflection, what you have is the value that you're going to graft in, together with the continuation, the rest of the computation. And that's exactly what the bind of the monad has. Okay, and once you make these definitions, you can then prove, and this is formalized, that F simulates mon on the nose. So for every transition that you have in the calculus for monadic reflection, you have then a sequence of corresponding transitions in the calculus of effect handlers. Okay? And it does not preserve typeability, and that's because this reflection operation can occur at any type, right? At this point, it can be a bit. At this point, it can be a function. This is exactly what this counter example does. It's a reader monad that has two cells, and I can use reflect at this type, at the bit type, and another one at the function type. Okay, so this reflector operator has to be polymorphic, and we did not include polymorphism in the core calculus. So if you add polymorphism, we don't know. Maybe you could do it. Okay, again, be very suspicious. Delimited control. That's a bit an older way of encoding effects and more established in a sense. So here we have two delimited control operators, shift 0 and what's called $. So there's quite a lot of delimited control operators. We chose the one that's closest to the other abstractions. Okay, so again, change the delimited control operator, bets are out the window. And what the shift operator does, so how do we implement the get? Whenever someone asks to get the current state, what you do is you shift, you get to the enclosing delimiter. That delimiter should have the current state, which is what this lambda does. It takes it. And then once you have this state, you give it back to the continuation and keeps this state floating around. Same thing for put. So you can contrast this with the handler implementation. That's very similar. Okay? And when you run it, when you want to run a state, what you do is you instill a new delimiter that's going to catch all those shifts. Okay. And the type system now, the type and effect system, has to track a stack of possible delimiters, all the delimiters that are on the call stack. Okay, and so it has to keep track of the types that are currently on the stack in order for things to match up. And this is what we have here in this case. So what we have here, what you're expecting is once you catch the continuation, you have to give back a function from bits that return a bit. Okay. And this translation is quite a lot more involved, and the full intuition is in the paper. But what we're doing here is we capture the continuation. So whenever we have an operation, we capture the continuation. The environment has a handler waiting for it, so we take that handler, and then we dispatch this handler over some encoding of the current operation. This is what happens here. So you have to have sums in your language to express this. Again, dubious about the design space. And when you walk through all the details of this translation, you get that the delimited control can then simulate F after congruence. So this macro translation simulates things almost on the nose. So this means we have thunks after the reduction that once you run those thunks, you get exactly the same values. Okay, and I'm not going to talk about the inexpressivity result because I'm out of time. So if you want, you can ask me about it. And that's it. So full data is in the paper, and the takeaway message is, if you're going to talk about expressivity, be very dubious, ask for a formal calculus and a formal proof. Thank you.